And this is our pre-break.
I think it's the 14th, by the way.
Oh, did I say the 12th? Yeah, the 14th. Yeah, this is where my head's at. The pre-break, post-Stull and Seeger discussion. So it's not a requirement that you got through this lecture. I know it's only been up for 2 days, and there's a lot of information in it. But if you have been through it, you now know why I wanted to give you the opportunity to ask questions, because this is a big deal as far as how this is working, and sort of what we can start to think about and conceptualize glaces. And obviously there's a lot more to come, as this is only the halfway point. But, you know, I wanted, you know, to sort of put you in a place where you're thinking and brewing questions as we head into our little break, and we'll return in January. So, show of hands. I know Dawn got through it. Anybody else get through the new lecture?
1 hour's worth.
1 hour. That's okay. Well, we'll let Dawn dominate the questions.
I stopped at runny glazes.
At runny glazes? Oh, okay.
I got to runny glazes.
That's not a bad place to be, actually, because let me pull up. Yeah, you're a good portion in. What else are you missing? Oh, matte glazes is really what comes up. So
yeah, where you started at matte. Yeah.
Right. Actually, you're most of the way through then. So, do folks have questions? Or you just want me to prattle on?
You know, I thought it was interesting on that chart when you were talking about the cones and firing your kiln, and about, like, I think, is it the rate? And just some of the numbers that you were indicating, because I was curious. Yeah, like if you could maybe talk a little bit more about that. I don't think I understood all of it, but I think it's really interesting.
Right.
And you said you like to go fast, because right now I'm firing a little kiln, and I want to know how fast I can go with low-fired paper clay. They're little beads, and I want to get it going reach 04. So I'm interested in when it comes to speed and stuff.
Are you bisking?
I'm just bisking, and and I have just got a new infinite switch, so the lower temperatures are hard to, I mean, the lower numbers, I'm not getting much heat. Right. And so I have to go higher, but really I just want to fire them. They're tiny.
Right.
So I'm sorry but yeah. I was wondering how fast I can go on this.
Okay, so there are, I mean, how fast you can go is how fast your kiln will go.
I mean, I could bring it Riley up to 10 after like 4 hours. I mean, and then just let it go, or because I'm slow. I have a manual kiln. I'm used to going slow.
Right. I mean, the thing I will say, and I know I mentioned the porcelain tiles, right, in the lecture of, in the tile industry, they will fire porcelain in 35 minutes from cold to cold. So that's 17 minutes from room temperature to cone 10. So our materials can take the stress. Now the big exception is if there is a lot of variation in your work, or but wait, in bisque, you often do need to go slower.
Yeah.
Okay. Because especially if you're dealing with paper clay, you do have a lot of burnout. Okay. You don't want to force that. You need to make sure things are completely dry.
Yeah.
And you see it all the time where somebody's got a pot and they had an explosion and they're like, oh no, it was dry. No. It wasn't. If you had an explosion, it wasn't dry. And I don't care if you left it sitting around for 6 months. There was moisture in there, and moisture can sit around if you don't force it out one way or another.
Well, my burnout's at 451, so that's kind of my key number, is burning out all that organics.
Is that actually the temperature?
I don't know. Who knows? Around that. I can smell. When you're talking about
Fahrenheit
color,
451.
Yeah, exactly. But I think it's interesting because I do go by color a lot, and now I'm probably realizing I'm going to go blind. After you're saying that. But yeah, I go by color when I monitor my kiln, and also smell. So besides looking at
yeah, I mean, if you're literally burning stuff out, then you can go by the smell. So anyway, but with bisque, you do need to go a little bit more controlled. Okay, because you're dealing with the moisture. Moisture is your number one enemy. Okay. Like I said, if there is any moisture, there'll be an explosion.
Yeah.
But
hang on. What are you up to?
If there are variations in thickness, right, that can also be a problem because you need to get heat penetration evenly throughout the work.
Okay.
But
Where's your
that said, I will, for my glaze firings, right? I will take a glaze firing and do it in 4.5 hours to cone 10. So, got to do the math real quick. I think it's 300 degrees in it. I think that comes out to 300 degrees C. It's 5 degrees per minute. 5 degrees C per minute. So almost 10 degrees Fahrenheit per minute climbing up. And it's not a problem. But again, I'm talking generally about pots, generally work without a lot of variation from thick to thin, and generally with a consistent thickness as a whole. Okay. So there's that. But you know, there's so much paranoia. Oh, you go slow through here and then you stop for quartz inversion. And then you stop. Like I was in a discussion the other day with some people that were talking about cristobalite inversion. Cause you know, like you go on some of the ceramics groups out there, and I won't name any, but if you're online, you might have visited some of these groups, and you know, you get all these threads of people like, oh, what temperature do you open your kiln? And people like, I don't open it until it's absolutely cold. And it's like, I always post a response. I go in as soon as my gloves don't burst into flames.
Me too.
You know, because there are all these, my glazes are pinging. My glazes are pinging. Yeah, because you're getting crazing. But as we'll discuss later, if you're going to get crazing, and actually as we talk about in this lecture, if you are getting crazing, you are going to get crazing every time. Okay, that is a fact, right? There is no way around that. If you have crazing, you get crazing. It is a physical chemical response between the thermal expansion of your clay body and the thermal expansion of your glaze. By pulling your pots out or opening the kiln when it's hotter, okay, all you're doing is making it happen faster. But you cannot stop it by slow cooling. It absolutely will happen. Okay. Now there are things you can do to get around crazing, and that's where we're going. You know, that's part of what we're talking about, is because crazing is on Stull's map, that we can define the chemistry of crazing. We can define the chemistry of thermal expansion. And this came up with a question from Peter. Well, I don't remember whether it was in our discussion last week or whether it was in the message boards, but you know, whether or not that crazing can be, or whether thermal expansion can be measured in a glaze. And no, we can't measure literal thermal expansion, but we can measure the changes in thermal expansion through behavior. Because if we look at a glaze and say, this is crazing, we can tweak it very subtly to get rid of it and to inherently change the thermal expansion to make it fit better. And that's all on the map. That's what's so amazing about this map. Go ahead.
So part of the question was with thermal expansion is that what's the thermal expansion of the clays themselves? In other words, right, you know, if you knew that this thermal expansion of this clay was really low and the glaze is really high, or vice versa, I mean, then not that you're going to have an exact number and match them perfectly, but that's why I was curious as to whether you could find out what the thermal expansion of the clay itself is. And I know you change things with the glaze, not with the clay. But if I knew the clay, then I knew more about the glaze, I would think.
The catch is you could change the clay just as easily as changing the glaze. Nobody does, because most people are using manufactured clays, or we have so much of a clay and we're so invested in it, it's not within our interest to change the formula of the clay. But you could change the thermal expansion of the clay or the glaze. Now, the first thing I'll say, as I mentioned to you before, and I don't want to get too into the weeds of thermal expansion, but that all the numbers you see of thermal expansion are completely made up. They're completely bogus and complete hokum. Okay.
The article you had us read implied that you could do some idea of figuring it out. And granted, there was a caveat. It's not going to be perfect. It'll be roughly around there. Right.
But where I want to go, and what the Stull map allows us to do, is to make those adjustments without having this number of, this is my thermal expansion number in my head. You can look at actual performance and go, okay, I need to move this way on the map just a little bit to alleviate thermal expansion problems. Okay, and we'll talk about that a lot more as we go. But the whole addiction to this actual number is a problem because, and I love numbers, but to assume that the numbers that a calculator is giving you are real is a fantasy, because that's not how thermal expansion works. And again, I don't want to go too much in the weeds, but thermal expansion is the actual expansion of a material. Okay. The problem is the way the calculators work is they say, here's the thermal expansion of silica, and I've got 20% silica. So I have 20% of the thermal expansion of silica. And here's the thermal expansion of alumina, and I've got 15% alumina. So I've got 15. So, and then they add it all together. The problem is here's the trick. Here's the mind F, is that silica has very high thermal expansion. But when you melt silica into a glass, it actually has incredibly low thermal expansion. So that number instantly becomes garbage because it has no reflection of reality. And you know, it's well documented as to that doesn't work. But what Stull tells us is, I've got a glaze and it's crazing on this clay body. How do I tweak this glaze to make it fit this clay body? And it's a very simple tweak. Very, very simple. And we'll talk about that in the lecture. I'm trying to remember whether I actually get into that into the end of this lecture or the next. No, it's in the next lecture, first lecture after break.
I have Peter locked on my main screen. Is everyone else getting that same
Oh, is
thing?
he not beautiful enough for you?
Yeah. I like seeing you, Peter.
See, I always, okay. Is it me now? Okay.
No,
No, it's not me?
I'm just getting Peter.
Still Peter? Is anybody else getting me?
Yeah.
I think it's
It's
you,
Denise.
Denise.
So how do I just want to have to be able to, because in case you
my
show.
picture.
Or click
Click
my
my
picture.
Okay,
Yeah,
click
click
ears.
Matthew's picture, right?
Yeah, you're not coming up, man.
At all?
Not at all. No. Am I? Oh, now you did. Now you did. Okay.
Okay.
Thanks.
Okay, there you go. Okay, so anyway, I don't. We are going to get more into this subject, so I don't want to go into that too much because actually, I still haven't answered Denise's question about fire temperatures and rates. Don't worry, I haven't forgotten you.
It's okay.
So we're going to get to the thermal expansion problem. But anyway, what we were talking about is the whole notion of when you're opening the kiln and heating rates and all this. You know, some people will say, oh, well, you don't want to open the kiln too fast because you're going to shock the bricks and the elements. Yeah, that's nonsense because bricks and elements are made to go to variable temperatures at once. In fact, that is the exact nature of bricks, that they're really hot on one side and really cool on the other. Okay, so as to what you can do with your work. The other one is people will talk about quartz inversion. They will say that quartz inversion is the reason why to not open my kiln. Well, quartz inversion is a real thing at 573 degrees exactly C, which is probably hotter than you want to be opening your kiln anyway. The remaining quartz in your clay body goes from alpha to beta quartz. It changes its physical structure, and it has no effect on your work. Okay, because here's the thing. Quartz inversion happens exactly at 573 degrees C. What that means is that if the top of your piece is at 573 degrees and the bottom of your piece is at 574 degrees, the top is going through quartz inversion and the bottom isn't. Okay, so any variation in temperature in the kiln would affect quartz inversion. And guess what? Everyone's kilns are going through that every firing, and people's work survive all the time because quartz inversion is a myth that people have made up to explain why their piece didn't survive the firing. Oh, I made my work perfectly. I'm amazing. But it died in the kiln, so it must be quartz inversion's fault because somebody told me that was a thing. Just like cristobalite. I'm the perfect potter. Perfect. How could my work have died in the kiln? It was cristobalite. Yeah, well, cristobalite, sure, it happens, but it takes 48 hours at temperature for cristobalite to really form. So is it cristobalite? No, you didn't make it that well, and it's your fault. You just don't want to take the blame. So anyway, go ahead.
Okay, thank you. So I have Val Cushing's glaze firing that I've been going off of. And that's bogus?
Next question.
Myth? Myth? Okay, fine.
I love Val. No. And this is the same thing. Look, okay. I am Val and Daniel Rhodes are my predecessors. I now teach their course. And I think the top 2 books on my book list are Clay and Glazes for the Potter and Cushing. There is a lot wrong with the information that they put out there. Now, am I saying, oh, you should absolutely rock it through? No, because my first caveat is if there are variations in thickness, if there are variations that are of concern, if your kiln doesn't heat evenly, because let's not forget that it's not just about the work. If your kiln has massive uneven swings, you do want to try to keep it homogenized, top to bottom, back to front. So going slower in earlier parts of the firing will help your kiln normalize heat. Okay. But as far as the step up to this and then slow down, and then step up to quartz inversion and then slow down, no. Nope. Now. Yep.
How much earlier? I mean, at what point do you feel like, well, let her go, let her sail? Because I mean, we candle overnight,
right?
And
candling overnight's not terrible. Well, if you're bisking, candling overnight is great. Like I said, number one concern when you are putting unfired work into the first firing, that is the explosion zone. Okay. Right. And again, if you okay, let's see. Here's my wonderful Scotch Elich mug that's all blown out in light. This right here is a thick spot. Now, actually, he's done a crafty little thing of carving out a notch right here, so it's not as thick, but, he's got a thick handle. So now I've got a spot here, the cross section of the mug and the handle where it's thicker. Okay, so that is inherently retaining more moisture or releasing it more slowly, I should say. So is there a benefit from a slow candle? Absolutely. Will a slow candle let you go to bed and come in and have a kiln that's at 600, 700, 800 degrees? Yeah, absolutely. That's great. That'll save you time the next day. Is it benefiting your pots? Getting low homogenized heat when heat's really uneven is a good thing. But is there some chemical benefit? No, not really. Now, if you've got things like if you're going to do a body reduction, okay, and body reduction is a fine thing to do. If you're working in any sort of, if you're going to be reducing, I encourage a body reduction, even though, because body reduction has some benefits. Iron, red iron oxide, which is a natural contaminant in all clays, even the purest porcelains have red iron oxide in them. Iron naturally converts from red iron oxide to black iron oxide at cone 4. And it happens instantly. There's nothing you can do to stop it. Okay. If you've got about under 3 to 4% iron in your clay, for the most part, it's not going to be an issue. If you have over 4% iron, okay, it can bloat during the firing because the amount of time it takes for that red iron to turn to black iron, you release oxygen. If that oxygen gets trapped by the glass forming in your clay body, that then becomes bloat. Okay. And so body reduction is an attempt to force that conversion earlier in the firing when the body is very open and porous. So the oxygen has plenty of time to escape. So you're doing it at 010, 08, somewhere in there. So slow down for body reduction, especially if you've got a lot of iron, but other than that, you can slow down at peak reduction as well if you want to get more reduction into your glazes. But at the end of the day, your reduction period really only lasts from cone, depending on how aggressive you are, cone 6 to cone 9, and then a lot of people will flash oxidation right at the end, which does often have nice color effects. So you might want to slow down for that to get more time in effect for your glazes. But I mean, as far as, how fast you can go, the main problem is going to be keeping your kiln even. Okay. Cause if you rock it and, say you get through body reduction and you rock it on up and you get from cone like 04 to cone 7, say you do it in an hour. Well, that's fine, but again, you have to worry about top to bottom because all the pots in your kiln need to be at that same temperature when you get to the end of the firing. If you get to the end of your firing and the bottom's at cone 6 and the top's at cone 10, no good. So it really comes down to keeping control of your kiln more than keeping control of your pots as far as your heating rate and all that. Now, for me, with my laissez-faire attitude, I'm an oxidation guy. I'm an electric kiln guy. And so, yeah, let it go. I mean, you know, for the most part, my kilns are pretty even, and it doesn't really have an effect. I don't have a big kiln. The bigger the kiln, the more you're dealing with that heat management problem. I'm not dealing with reduction. I just go. I don't have to slow down. I don't have to pause. So yeah, I will go from, you know, if I have a kiln that'll do it, like when I say I'll go in 4.5 hours, those are some of the higher end kilns at school, you know, but in general, I turn it on and walk away, put it on fast, whatever. You know, I'll monitor it with cones and monitor the pyrometers, but I don't baby. But again, there are always conditions to,
Could you go back? You said something between cone 6 and cone 9, and I missed what that was.
That's generally where people are doing their glaze reduction. Kate, you know what temperature you generally push reduction for your glazes since Phil disappeared?
8. Cone 8.
So you go into reduction at cone 8?
Honestly, we reduce all the way from body reduction up through cone 10.
Right.
Mildly, and we push it hard at cone 8.
And that's pretty standard.
I have a question.
Sure.
Yeah.
Yeah, go ahead, Kate.
Okay. And this could be totally wrong, but the Pinnell method that I learned is you have to catch it between like 014 for your chinos, and once the glasses are formed in that glaze, like around, I don't know if he said like 1 to 3, they're pretty much locked in at that point, and you can reduce all you want, but that's not gonna. And I've seen that personally when my own kilns shut down and I had to open it up the next day. They were copper reds, but nothing had turned to glass yet. Like the blushing was there, the colors were there. I
will answer that question in 1 second. Let me go back to the
6 to 9 to me honestly doesn't make any sense except for just evening out your kiln. That's what I thought.
Well, okay, so back to Robin's original question of generally, so what Kate is saying is generally what people do. You'll push body reduction, then they'll push into sort of a light reduction neutral to fire up to temperature. And then at the end, look, what I was saying from cone 6 to 9, or she's saying from cone 8 to 10, she'll push it into a heavier, what they'll call glaze reduction through the end of the firing. Now, some people, like the copper red people, will flash oxidation for cone 9 to 10, where they will literally pull it out of reduction and let the oxygen flow into the kiln. And for copper reds, it actually does have quite an effect. It will make the glazes much more lustrous. So that's just the basic process that most people will do for reduction. So there'll be body reduction, and then they'll sort of somewhere between. Now, actually, I hate to use the term oxidation because actually you never get oxidation in a gas kiln because gas kilns are based on combustion, so it's always neutral to reduction.
Okay.
So then to the other Kate's question, there is a theory out there that once your glass forms, and as I talked about, that's really the last 100 to 150 degrees C of the firing. That's what I talked about at the beginning of the new lecture.
Okay.
The theory is that you don't have any effective reduction. Okay, meaning that reduction is you're taking a carbon-based fuel, natural gas or propane, okay, and you are forcing the oxygen out of the flame. But a flame needs oxygen. It must have oxygen. Heat, fuel, and oxygen is what you need to create a flame with a natural gas source or with a combustible source. So if you remove the oxygen, you only have flame and heat. So you need to get oxygen. So what happens is the carbon atoms, okay, are then broken apart from the natural gas, and they extract oxygen from wherever they can get it, from the ware, from the shelves, from the bricks, okay, from anywhere they can get it. And the thought is, once you formed a glass in your glaze, that reduction can't penetrate, that it can't pull oxygen out. And I'll tell you what, Kate, I used to think the same thing. But actually, I have found, and I have been told by some of the engineering professors, that is actually not true, that the reduction can penetrate the glass matrix.
Okay. So if you miss the beginning stage at the 014 to 04 reduction, like the body reduction,
Okay.
and can you set glaze reduction then at 6 to 9 and get anything?
Yes.
Okay.
Okay, hold on. But there's classification. You started by talking about Chinos.
Yeah.
Phil, you're on time to delay. You're in two places. Oh no, I'm looking at your camera down and paid above. It's surreal. Okay. Chinos are a slightly different case because Chinos are a very odd glaze compositionally.
Right. We would just do it low to just because of a Chino, but I'm just talking like say a Celadon or whatever.
Right.
I mean, okay.
Well, so then it comes down to how you're pushing your reduction, what type of clay body you're on, all of that type of thing. But yeah, I am fairly comfortable with a high temperature reduction.
Really?
I'm actually more skeptical of the needs of a body reduction.
Well, yeah, they didn't. Started, or Pete started to say it's really not like one and like two different things. It's just you got to get it locked in early to then get it set, and the rest of reduction is basically to even out your kiln, not to necessarily force any kind of chemical thing to be happening to that glaze. So
the evening out the kiln, that's an interesting concept.
Or or to just basically that, I guess I don't want to misquote anybody, but I mean, I totally believe that, there are many different things that have been found out there since I graduated and stuff. So I'm totally open to what you're saying, and I want to learn more. But I just don't, and I don't want to misquote what Pete said. Yeah, it was like basically once you miss that window at the kind of early on, the only reason for having it fire inefficiently is if you want to have a slower kiln, if you want to keep it kind of the unevenness or just reduction isn't necessarily to keep kind of hammering away at the glazes. It's kind of done at the beginning, and if you miss it, you're done. You're not going to set a copper red late. You're not going to set a Celadon late. And I mean set by get that
problem is, okay, so
and I don't want to.
Copper reds will come up later.
Okay.
Copper reds are hard to talk about because they are actually Kate, I'll get to you in a second. Other Kate. Copper reds actually need multiple stages of reduction.
Okay.
And that's just because of the nature of copper reds. And this will come up in a later lecture. But the short version is that copper reds have to go through multiple actually stages of reduction to get to red, because it goes from copper carbonate to copper oxide to copper metal.
Okay.
And you have to force those different stages through the fire.
Wow. Okay.
As far as Celadons, or just reduction in general, again, it really depends on what you're trying to do with the glaze and with the body. What's your iron content, and are you afraid of bloat? The next thing,
I'm always afraid of bloat. Just put that on the record.
Well, I have a lot of water retention issues myself. So say you're firing a porcelain, okay? Man, back when I ran a small clay company, I had such issues with this because I was making porcelains, and I would get hammered by the porcelain snobs about the whiteness of their porcelains. Okay, because the porcelain, has anybody here a porcelain snob?
Me.
You. I love the porcelain snobs. But that porcelains have two ways of existing. Okay, an oxidized and a reduced porcelain.
Okay.
And the whole catch is that, like I said, all clays have red iron oxide in them, naturally occurring, even a tiny, tiny little percentile.
Mhm.
Small percents of red iron oxide naturally look orange, okay, or yellow. So if you fire an oxidized porcelain to cone 10, it will have a yellow tint to it. Reduced porcelains will have a blue tint to them because you have converted red iron oxide, which is giving you a red, which when you dilute it with enough white, it turns into a yellow. If you reduce red iron oxide, it becomes black iron oxide, and you dilute that enough and it looks blue. If you put and you have to understand that for white, like just for like, you know, if you're looking at a piece of paper white, you can put this in front of some color people and they will debate about the quality of this white for hours because there is no such thing as a pure white, but there is perception of levels of white. And it is well known that people perceive a blue white to be much whiter than a yellow white. And they are also known as hot whites and cold whites. Cold whites comes across as whiter to our eyes. They both have the same amount of iron in them, but by reducing that tiny fraction of a naturally percent of naturally occurring iron, it will make it look whiter. Okay. So again, this is the question of where you're getting reduction, what you're trying to get out of your clay, what you're trying to get out of your presentation. So, you know, like I said, my general procedure would be whether or not you want to do a body reduction. And I'd say you could probably skip it if you're doing a very low iron clay, but there's no reason not to do it if that's what you're comfortable with. And then a high temperature glaze reduction. And again, most people's procedures are kick in heavy reductions somewhere from cone 6 to 8 up to cone 9 or 10, and then decide whether or not you want to oxidize it again at the end, which will generate brilliance in some glazes, okay, to reoxidize it at the end, to flash it. But, you know, that the subtleties of it are really depending on your glazes and the colors you're trying to generate. And a lot of that conversation we're not quite at yet, so.
So Matt, I have a million myths that need busting, probably.
Oh, okay. Hold on, wait.
But-
Let me see what's your text here. Related, inducing reduction with a power burner.
That's Phil.
Oh, that was Phil's question.
We fire in kilns that have power burners.
Right, forced air, you mean?
Yes. And as you increase air, you're going to be increasing the air pressure inside the box. And pulling a brick and seeing a flame come out does not necessarily indicate that you're in reduction any more than you might be otherwise.
Do you have retardant panels on the blower?
No.
See, the way most people I know, most burners will have, so there's an air intake on the blower, right?
Yes.
Okay. Most people will just, a lot of burners will have a little metal door that you can close over that blower. So you're literally letting less oxygen in, or some people will just take a piece of paper.
It has a disc
We have valves that we can.
that covers some of the opening,
Right.
so that the orifice, if you will, of the air going into the
Yes.
fan is somewhat constricted. And then the control of the air is by a simple gate valve.
So there's a valve in between the blower and the mixing.
Yes.
Okay. Can you push it to black smoke?
Yes.
Okay, then that's all the reduction you ever need.
Okay. So if I'm just looking for a little bit of soot for a brief period of time, I got it.
Here's the trick. You don't even want any soot.
Because then you get carbon trapping?
Nope. Because then you're wasting natural resources. Because here's the deal. Okay? When you're reducing, again, you're extracting oxygen and you're forcing combustion to happen through other means. If you're getting black smoke, all that is you are literally pushing natural gas into your kiln, breaking the carbon bond in the natural gas, and then you're just throwing that carbon out the window. And so you're literally just taking natural gas, burning it, and throwing it out the window. It's like extra pollution.
So what's your best determinant for knowing that you have reduced in the kiln?
Well, I mean, I'm a numbers person and cold and analytical like that, but I'd say get an oxygen probe.
Yeah, we don't have that option. So what else you got?
Well, you push to black smoke and then you pull it back a hair.
Ah, there you go.
So yeah, you push it to black smoke to confirm that you've got solid reduction. But I watch these kilns where people are just dumping black smoke out, and it's literally just burning natural gas and just like sending it out into the atmosphere. So you're not only wasting the gas that came out of the earth, now you're dumping extra carbon into the atmosphere. You're doubling down on global warming, 2 times the fun.
We get a little bit of soot once in a while, but we just.
Okay. Are you satisfied with your reduction?
Our firings are very nice.
Yeah.
But my process is very precise and different from what you're recommending. So, and I fire a lot of student work. So I don't want to change a thing until I know that that's okay.
Well, now the student work is different. Okay. When you're dealing with the public, it's the same thing with you don't just load a kiln with bisque pots for students and then you just fire right up. They're lying to you about how dry that stuff really is. So you take it slow. You'll make sure it's even. With the student work, that's different.
But we already have the work bit. That's not the issue.
Well, I'm just saying in general, with the same thing with the application with the consideration of if it's all your pots and say it's all mugs, how thick the work is, how good your trimming is, how, all of that type of thing, how well you stack the kiln, how evenly it's stacked. So, you're going to get even heat penetration throughout the kiln. You're going to get good airflow throughout the kiln. So your reduction path, the path of the airflow will be even, all of that, then, do whatever you want. That you don't have to be as conservative. If it's other people, yeah, be conservative because that you're going to get blamed. And this, again, sort of going back to people blaming the kiln, if anything goes wrong with somebody's pots, the person who ran the fire and gets the blame, even if it was 100% their fault. It's a trap, but what are you going to do? Yeah.
So here's my questions then.
Okay.
But here's some many thoughts. Okay, so we go up to this magic number 1180, which was Val Cookie's number, I think. Fahrenheit? No, that's centigrade. No, Fahrenheit. Hold on a second.
Hold on, I'm pulling up a cone chart.
Hold on.
Oh.
So, go ahead.
1180F. That's super cold. That's 020 if it's F.
Yeah. So just to go very, very gradually, I go gradually up to a little bit beyond 1200 F. And then, I let it ride. I go fast until just when 010 starts to tip. Then I throw it in reduction.
Okay.
Then, because I believe that's how we get our toasty brown stonewares.
Okay.
Am I wrong about number one? And then through 010 to 08, I keep it in reduction. I try to keep it at about an hour, but it's usually a little less just because that's what the kiln is doing. So then at 08, when 08 goes down, I can ramp it. I let it ride until I keep it in a mild reduction all the way up to cone 8 when, as we talked about, I reduce.
Push it heavy.
Push it, a heavy reduction. Yeah. And then at cone 9, we spray soda.
That was my next question. This is all in atmospheric.
Cone 9 is even, it's all atmospheric firing, and it's even top and bottom.
Mm-hmm.
And so it's like really working on getting that even just before you spray soda.
Which again is one of the important details about how fast you go of trying to keep things even. Now, we all know that it's always a struggle, and then as you get up to higher temperature, things start to even out. But you don't want to go and ramp super fast and then end up at cone 7 or 8. Who's getting a phone call?
It's my landline.
You don't want to get up to cone 7 or 8 and realize that you're 100 degrees off top to bottom, because you're then going to stall out and spend the next hour trying to get those temperatures to match before, you hit cone 10 at the bottom, and then you got to shut down because you can't go any higher. You don't want to nuke the pots at the bottom. As far as the quality of oxidation, your clay, the color that you want. And if you're comfortable with the reduction cycle you have, use it. Is that necessarily going to be required? Not necessarily.
I sure would like to get done sooner. So we started at 4 in the afternoon on one day and end anywhere between 4 and 10 the next day. And if I can get that to shorten without injuring the pots, that'd be great. But
well, are you just controlling the size of the flame coming out? Are you just trying to keep it going slow, or you really think that amount of reduction is giving you what you need?
I'm timid about running it too fast. I think I can keep it even, and I think I can run it fast, but I was concerned about a lot of the stages, especially during reduction, going slow through reduction.
You want to go slow through reduction because you need to penetrate your material, and you need time to get a homogenized exposure. That's why I said, if you're doing a body reduction, you go slower, that you can slow down in there and take your time, because you need to get a complete body reduction. If you don't, let me see if I can find a picture real quick. Hold on. Glazes. Okay. Now let's see. Let's share this. This isn't a perfect example, but the consequences of uneven reduction, okay, is this, right? Wherein you get incomplete reduction in your body, and you get 2 different states of reduction. Now, this example is not perfect because this is in a very high iron clay in a very heavy reduction, but what you can see is that this is heavily reduced on the outside, and this is very, very lightly reduced on the inside. Okay, and this pot, the reason why it's cracked is it dunted. It literally shattered on the cooling because he's got 2 different, basically, thermal expansions trapped inside one clay body. Okay, and this pot he was having problems because his foot rings were actually not getting enough reduction because they were sitting so flat on the shelves, and he had so much iron in his clay, so we really had to work with getting his timing just right to get a completely permeated reducing firing. But I think this body, he ended up with 6% iron content. He was really trying to get a dark body. But that you fall into this sort of danger if there's a lot of iron in your body. If you're just saying you just want a toasty stoneware, the odds are a lot of your toasty stoneware, because the crazy thing is, no matter how much we think reduction, you'll notice a lot of stonewares will have if you break them, will have a different color on the absolute surface than they do on the inside. That's because the iron is actually unreducing on the cooling. It will convert back to red iron oxide right on the surface. Okay, because as the kiln shuts down, although we have stopped adding in fuel, that doesn't mean that combustion has stopped. And although we might close up the burner ports and shut down the damper, it's still sucking in as much oxygen as it can from the atmosphere, and the surface of the pots will often oxidize from that, which is why you'll get a certain color, especially say on exposed clay, like on a foot ring. So getting that balance, really depends on what you want and where you're trying to go. But again, that your Can you go faster? Yes. I would probably rely on the body reduction and the final reduction, but if you want to go faster through the middle, set your middle reduction at a level that you're comfortable with and ramp up the size of the flame as long as the kiln is staying even. I would feel pretty comfortable with that, but try it and see. Again, it depends on your clay, the iron level, your kilns, the evenness. How leaky are the kilns you're using? Are they pulling in oxygen in between the bricks, in from the stack, in through, are the ports completely closed off? All of those types of variables do have an effect. Like you're saying you used a forced air burner. Do they have a metal cap that literally attaches the burner to the wall of the kiln? No. So again, that's an area where actually you're pulling in a ton of oxygen. And so these types of variables can really have an effect. But, can you fire faster? Yeah, sure. Don't just jump off the cliff and say it's going to be fine, Just experiment going a little bit faster through that middle ramp, and I think you'll probably be okay.
So
Thank you.
Matt,
Yeah.
if you have that because that the carbon coring example you showed, so to solving that would be to just do a longer, slower body reduction, and then basically, with it, like let's say you were just trying to have, because I've seen that problem a lot, right? And it maybe not so dark, not so irony a clay body,
right?
So would the solution be to just like do a slower, longer, steadier body reduction?
Well, it depends. Okay, so actually, it's funny that you call it carbon coring, because this is not carbon coring.
Okay. Whoops.
No. That's the common name that people associate to this problem, but it's actually the opposite. Okay. So since we're talking about reduction and penetration, a quick discussion on that, and then I thought we were talking about glazes, but anyway, so what happens is, again, you've got red iron oxide, which converts to black iron oxide. It happens naturally at cone 4, and as you proceed, it doesn't happen instantaneously. But as you go from cone 4 and climb, red iron converts to black iron naturally. Okay. And what you get is that you then form 2 types of glass, because a fired clay body, as I discussed, is basically mullite and glass. Okay. But the thing is you can form different types of glass. And you form what I would call black glass and white glass. Okay. And black glass is glass that has black iron oxide in it. And that has 1 thermal expansion. White glass, okay, is glass that has red iron oxide in it, and it has a different thermal expansion. So now actually let's that's a better one. Let me see if I can find a better picture. Hold on. Oh, you guys can see my playlist. My rockin' 80s playlist. What's a better picture here? No, that's slightly better. So what is going on is, what the problem that he had, right, when he first came to me, was that this guy was making bowls and plates that came out just fine, but his jars were cracking. And his jars were cracking because literally he couldn't get reduction into his jars. The seal between the jar, which with the lid on was essentially airtight, was not getting a reducing flame, whereas the outside of the pot was in heavy reduction. And so that was converting the red glass, the white glass, into black glass. And so on this picture, this is the outside of the pot and this is the inside. And so he gets these 2 different thermal expansions and they would crack. So how did we get it with him? More body reduction. Also with his jars, because he had so much iron, he had to start firing without the lid. And just, do his best to make sure that they fit together later. And of course, the irony came in of his bowls were just fine. Why? Because his bowls didn't have anything blocking the reduction on the inside and the outside. So he got a complete reduction. But again, this is based on a lot of iron in his clay. Like I said, I'm pretty sure this was 6%. Okay. If you're under 3%, you generally don't have to worry about this extreme of a problem. But yeah, as Ursula is saying, more body reduction, making sure you're getting complete exposure of reduction inside and out. With his, the one I was showing before, that he had the problem with the exposure of the thick clay here, okay, where he had a lot of massive clay. And even though he's getting reduction outside, he's not getting much inside, and he's not getting much in his foot ring because, again, this is blocking a lot of reduction from the kiln shelf, right? So he had this problem. So it becomes a geometry problem. Trim this down more, maybe put it on stilts, maybe put it on wadding, try to figure out a way to get oxygen or reduction inside that atmosphere. But yeah, this is definitely an extreme example. Did that answer your question, Ursula?
Yeah, that's good. Thanks.
Okay.
Okay, can I ask another question since we're asking random questions?
Oh, okay. Since nobody watched the lecture except for Dawn and half
I got through
Debbie.
half of it.
And half Debbie. Ursula got through half of it. Okay. Go ahead.
Okay, so with so part of me wonders, and this is an 04, and I know you hate 04. But,
No. Don't hate 04.
Okay.
Love
well,
04.
At 04, is there, so some of the glazes use black iron oxide and some glazes use red iron oxide as colorants. But there's nothing, so and they do behave differently. Like they do actually behave differently, but it makes no sense to me that they would behave differently because they're fired in oxidation. So wouldn't they all just convert to red iron oxide? So what is going on there?
Well, okay. There are actually two different types of black iron oxide. Okay. So there is FeO, which is what is happening when you're firing and it naturally converts. Fe2O3, which is red iron oxide, converts to FeO. Okay.
Okay.
Right. So it loses some oxygen and it becomes black. The problem is black iron oxide as a colorant is a completely different material. It's Fe3O4. So it's a different form of iron. And if you go back to the valences and you look at the different valences of oxygen, there's different ways that it can exist. And Fe3O4 is also a black form of iron oxide, but it's a different structure of the material, so it gives you different reactions. Okay. And then on top of it, at 04, you're not going through any reduction reactions. There's no reducing in an 04 kiln. Are you pushing reduction?
No. I'm just, no.
Right. So you're getting the true state of Fe3O4 and Fe2O3, and they're going to behave in different ways.
So wouldn't Fe3O4, I guess no, it wouldn't lose anything because it's just hanging out there.
And Fe2O3 won't lose anything either.
Okay.
Okay. And that goes, talking about the cones, right? Remember that the low temperature, the red cones are using Fe2O3, and they're not converting into anything at low temperature. Okay, they're working just fine, but melting as a flux, but they still stay as red iron oxide. So yeah, you're definitely going to get different effects from those two different oxidation states of iron at 04.
See, I always thought, I'm just, I guess I didn't realize that black iron oxide that you get in a clay body or in reduction kiln is FeO. I don't know why. I think when I did Glace Calc, I always thought, I remember them talking about Fe3O4. But maybe I'm wrong. I mean, I guess I'm wrong, so that's good.
Well, Fe3O4 is often called magnetic iron oxide because it actually has a magnetic charge to it. You can move it around with a magnet. But yeah, they're just different valences of iron. Now, if you went and reduced Fe3O4, if you put it in a high temperature firing, eventually it would convert, because when you talk about iron and oxidation states, the natural oxidation state of iron is Fe2O3. And actually, I'll have to find it on my on Ceramic Materials Workshop's Facebook page. I posted an article recently that was why are all barns red?
Oh.
right? And barns are red because red iron oxide is cheap. But it's also because iron is the last element to form as a star burns out. And we form a lot of iron very quickly. But it's the heaviest molecule that can exist in the nuclear reaction of a sun. As the sun starts to burn out, it's generally converting helium to hydrogen, but as it loses its heat, it starts to make heavier elements, combining different elements together, and then it makes iron. Well, that's why we have a lot of iron on the Earth. And as iron oxidizes, it will naturally go from iron, Fe, metal, into red iron oxide. And that's what rust is. So Fe3O4 has to be synthesized. It's not naturally occurring. And the same thing goes with FeO, fired black iron oxide. The reason why I was just saying to Kate of that pots will oxidize on the surface, on the foot ring back during the firing, is because FeO is not a particularly stable material. So on the clay body, on the surface, it's got time in the firing for reoxidation to happen. Now, in our glazes, we're relying on the fact that the glaze does eventually solidify and keep that reduction reaction in place in the glaze. But in the body, it doesn't really have as much of a seal as the cooling glaze does. So we lose a lot of the reduction effect, and it oxidizes on the surface.
Mm-hmm.
Yeah, iron's a really cool material. It's very bizarre. And it really controls a lot of our lives. In fact, in my Glazes 2 class, I have an entire lecture just on iron. Because it's just like, we can't get away from it. We can't escape it. You know, it's messing with our lives. But it's amazing too. I mean, the fact that you can get everything from the subtlest blue celadon, you know, to tea dust and oil spots and all that, and Temeku's, all from the same material, you know, oxidation versus reduction. It's really amazing. I mean, we don't necessarily give iron all the credit it's due. It really is a major player in everything that we do. Man, everybody's muted now. It's like I can make fun of all of you and nobody can say anything.
No, you can't. I can hear you.
Oh, Peter's not muted.
Yeah, I'm listening too.
Okay.
Can I ask one more quick kiln
Absolutely.
question? I was
Oops, no
wondering,
chemistry.
well, yeah, but I have both a Scott kiln, you know, larger one, but I also have a small AIM tester kiln, which actually I'm running right now. And I haven't done anything with glaze testing with it, but when you're using a test kiln, are there any tips or anything that you can get consistent results? Because that's what I heard, like at the Northern Clay Centers, their test kiln, they're like, they're kind of quirky. So I just wanted to know that if I'm doing tests with my test kiln, you know, for the glaze class, if there's something I should be aware of that might be different than a normal kiln.
Not if it's electric. I mean, you know, a test kiln will give you a different heating rate. And again, the thing to remember of, you know, all this of me saying of heating rate doesn't matter. Well, remember, I'm a liar, because one of the first things that we talked about in talking about how cones work is the fact that heating rate affects your firing temperature.
So we're coming full circle to my first question.
Absolutely. I was getting there. I told you I was going to answer your question. Right? Oh, yeah. So let's do this. Wait,
Good job, Denise.
okay. So, coming back to...
Which was in this lecture.
Right. Yes. We were
See, I'm coming back to the lecture.
I was getting to this lecture. Okay, so you know, the thing to remember about temperature that's so interesting. And now again, and I mentioned this in the talk, of a lot of people will talk about this whole heat work thing. Like people have to say, oh, it's just heat work, which is a load of nonsense. When people talk about heat work, they're just spouting off words that they've heard that sound really fancy. But because the important thing is that cones are based on chemistry. But it becomes then a question of what is temperature? And actually, not lecture 8, but lectures 9 and 10, we'll really talk conceptually about what is temperature, what is the value of temperature, and what are we getting from temperature, right? What are we doing chemically and heat-wise to get certain results? So we know these cones are based on a certain temperature. Well, they're based on that temperature because you're waiting for a chemical reaction to happen. right? That's the whole thing of, we know from our cones, you have a certain amount of silicon alumina and you need to get them to melt. That's the cone reaction. Well, you can think about this two ways. If you push it really fast, you still have to wait for the chemical reaction to happen. It's not like it just turns on. So you can either fire fast, and then you're going to need a higher temperature to get that reaction to happen, or you can fire slower, and the reaction will happen at a lower temperature. Okay, so it really depends on what you want to get out of your work. And again, that the swings are pretty extreme. Again, coming back to cone 10, in a fast firing, and this is not even that fast. This is 150 degrees C an hour. So I'll actually fire, like I said, in the fastest kilns at school, I will fire double this. Okay. But at the fastest firing here, 150 degrees C per hour. Zoom in on this a little bit more so you guys can see it. Can everybody see the numbers, or am I too like pixelated or something?
They're small.
They're small. Okay. So 150 degrees C per hour. And again, remember that this is for the last, where'd my cursor go? My colorful cursor went away. The last 100 degrees C of firing, which is the only time that monitoring temperature is actually relevant. For the last 100 degrees C of the firing, but also of that cone's range. Okay. So at cone 10, at 150 degrees C per hour, cone 10 equals 1305. Okay. At 15 degrees C per hour, cone 10 equals 1251. Which means, now 15 degrees C per hour means you are basically taking, it's like what, 6.5 hours to get through that last 100 degrees of firing. 6.5 hours to get through 100 degrees of firing. That is slow. Okay, but if you're making something crazy thick that you need to fire to cone 10, sure, fire it slow. Excuse me. But if you're going fast, you are, what, 54 degrees hotter. And that's to get an equivalent chemical reaction. And these two temperatures will give you an equivalent reaction at that heating rate. Okay, so my mentor, Dr. Cardy, who some of you guys have taken his thing, he's done a study about, excuse me, about Korean porcelains. And these are ancient Korean porcelains in dragon kilns. And they would only ever fire to cone 8, but they would fire at temperature for a long time. Okay, so although they were only firing to cone 8, quote unquote, by dwelling at that temperature for a long time, they are achieving a higher temperature reaction. So, you know, I mean, what's the application of this? Well, you know, as we're talking about here with Denise, you could fire slower and know what temperature you're going to. So, you know, this medium rate is 60 degrees C per hour, which means something along the lines of like an hour and a half for the last 100 degrees C of firing, that it gets you down to 1285. So if you've got your test kiln and it rockets, but your larger kiln goes much slower, think about that. Track your heating rates, you know, honestly, yes, sit there with a stopwatch and track how fast it's going, or get a video baby monitor and put it in front of your kiln and watch the temperature as it climbs on a clock. Okay.
Well, that's
and
what
then,
I'm having. Sorry.
Go ahead.
Well, what I'm having problems with is that I feel like I'm not getting any heat really until cone 5 right now, and then I have to go really hot in order to really get anything to happen. So that's why my small one, my test kiln, which I'm using right now, and so I got a new. I thought that would be a problem with the infinite heat switch then with that. So I just felt like, wow, it just seems like it's not doing anything until I, you know, put it at number 5, you know, and so I feel like it's a snail. And then all of a sudden I'll put on cone 10 not cone 10, I'm sorry, I'm using the cones, but the numbers. So I'm having a hard time when it comes to pacing it and as I turn things up. And I just got a pyrometer. I don't know if you can just stick them right in. So, I mean, this part's new to me, and I don't want to take anyone else's time, with it, but but when I'm doing glaze testing and so forth, I'm just trying to find out how to climb it, with a manual kiln. So
Well, I'm not a kiln guy, so I can't speak as to
Okay.
sort of how much heat you're generating at a certain time, like, ohms and heat output and all that. I don't know. That's beyond me. If it's a completely manual kiln, the best way to do it is you just, most people will say turn it up to 1, and then they'll let it sit for an hour, and then they'll turn it, whatever, you go up to 3, so you turn it up to 3, and then you run that for 5 hours, and then you run it up to 6. I think that the pyrometer is going to help you, because then at least you have a real number to reflect as to what your temperatures are. If you're doing it by eye, most people, if they're doing it by eye, will do it by a kiln sitter, Yeah, so in a kiln sitter, that they're real convenient, that they'll just shut it off when it gets temperature. Of course, kiln sitters, again, change the equation because they're actually hotter, coming back to the cone chart. Small cones for cone 10 is 1330, and that's because you don't want it getting to 1305 and shutting off, because that's actually under temperature. So you actually, the sitter cones are designed to actually cook a little bit hotter so that you actually get heat penetration through the kiln instead of just getting to exactly that temperature and shutting off. It's that you do have to develop a technique, and I think that the pyrometer, that's going to be your best tool. It's going to be totally boring, but yeah, like seriously, go on Craigslist and get a video baby monitor.
Yeah, I was thinking that today. It's funny you mentioned that.
I totally.
I was like, I should get a baby monitor. Yeah.
Yeah, I mean, I have these things. They're called Nest Cams, and they're like home security cameras, but they're web based. Mm-hmm. And so, like, I use them to watch my kids. But like, if I'm firing the kiln, I will take one and put it in front of my kiln, and then I can open it up on my phone and track the temperature. But seriously, keep a notebook. Just keep notes on what your cones are doing. I mean, that's the benefit of having a computer controlled kiln, is you put it in a rate, and the computer doesn't care how much electricity it's putting out. It's just trying to meet the rate, And so computers are a wonderful luxury, but if you're doing it by eye, it's taking notes. And then it's taking notes and doing math. Sorry.
That's okay.
Any other questions?
Yes.
Okay.
I think I have a chemistry question, and this is
no.
theoretical.
Didn't you just say no more chemistry questions?
No, I love chemistry questions. So.
Okay.
The question is more theoretical, and it has to do with the lab we just did.
Yes.
And so when we did the lab, I thought that it would be interesting, but I needed the skull and the molecular formulas to be able to do this, because all we're doing is changing weight when we change the various alkaline metals and alkaline earths. And so as a result, we're going to be changing the chemical mix there as well, not just changing out the material, the material itself. You're going to give more or less material than you would have had before.
You're giving away my secrets, but okay.
Okay, so that is what's going to happen. So I thought it would be interesting to look through. I guess I'm trying to figure out what, I was thinking through, like, say, lithium, which is supposed to be that much lighter. So there's going to be a whole lot more lithium in the one we changed out than, than the potassium that was in there.
So that's the next lab, Peter.
That's lab. He's talking about lab 2.
Yeah, that's.
Yeah, but I think he's projecting towards lab 3.
Well, if I had time, I was going to do that, but that would have taken me about 12 more hours than I had. So
well, I'm not going to discuss lab 3 at the moment, but yes, you're right that what I'm doing is tricking you to see the effect of molecular weight, and then go back and see how that affects the UMF. I don't remember the exact proportions of, say, lithium to potassium, but basically I do have it in my head that basically barium levels are double calcium levels.
Mm-hmm.
Okay, and this goes back to talking about the barium in the barium talk in the last lecture, of everybody freaks out about high levels of barium. Oh, is this too much barium? Is this too much barium? Well, what are you talking about? Because to say, oh, this has 30% barium, what does that mean? Right? When people don't put in 15% calcium and say that's too much calcium. No, they just look at a number and that they see that number is large, but without any perspective, it doesn't mean anything. So yes, I'm sort of short. This lab is I'm shortchanging you so we can see the results of how it has an effect and how it doesn't have an effect, because yes, that the secret answer is that we will then go and reverse engineer the chemistry.
Okay. Thank you.
Yep. Good observation. Any other questions?
Okay. So
Okay.
I only watched the first half. I have to be honest.
That's okay. You're
But
in
you
the
spent
lead.
you spent a lot of time talking about what the cones were made of, right?
Right.
Like how up to cone 10, O10, they're basically have boron in them that flux them. And then when in that middle section between cone O10 and cone 3, they have iron as the flux.
Mhm.
And then is it 3 on? Is that right? Am I saying
Mhm.
this right? Then they just become glaze materials, and they're just based on feldspars, right?
Yep.
Okay. So what is I got the different sections. I guess I don't understand why you put such an emphasis on it and why it matters so much that they're each created from different materials. Why does that matter to you?
Because those are our glazes. It's the secret of your glazes are hidden right in front of your face.
Busted.
No, but I don't. I still don't get it. I mean, like, so I don't know.
Because the low temps need more, I'm guessing, the boron-y stuff, and the high temps need the flux, the feldspars.
Well, it's not just
Maybe?
that. Because,
Oh.
hold on, wait, which slide am I looking at here?
And I don't get any of this, but I want you to repeat the iron thing you went about 40 minutes ago. Anyway, go ahead.
No, move on. Go
That's
back
how
and watch
bad
it.
I am. I'm like, what?
Because, okay, and I don't know how far you've gotten, but if you push it a little bit farther into the class, that what comes around is that the cones are literally just glazes.
Mhm.
Wow.
I mean, literally, like the cones are on Stull's map. Okay. They are 0.3 to 0.7 potassium to calcium, 10-to-1 silica to alumina ratios. Okay. And that's what's so important about cones is that since we're using cones to define temperature, that relationship is already in the glazes we're dealing with every day. Okay. Because no matter how complex your glaze may seem, right, no matter how many different ingredients, no matter what fluxes you're using, that it's still a very, very simple system of silica, alumina, and 2 fluxes. Okay. And so when we talk about the cone 1, cone O1 divide, right, that's really important because that really defines not just temperature, but what will melt. Okay. And that's super important because if we can't define what will melt, then, or I'm sorry, if we can define what will melt, then we can define the relevant temperatures to our process. Okay. And it's why cone 10 is what cone 10 is, because really it's the lowest possible temperature, believe it or not, even though we call it high temperature. Cone 10 is the lowest temperature we have where you can create solid, durable glazes, okay, with feldspar, alkaline earth, clay, and quartz. Okay, so without including boron, or without including lead, which is what predated boron, which will come up several lectures down the road of, I do talk about lead in that's what everyone was using for lower temperature. Because the Europeans had a serious problem. Okay. High temperature, specifically porcelain, was invented by the Chinese several thousand years ago. The Europeans didn't discover it until like 1715, I believe. Right in there.
1710.
1710. Exactly. Thank you, Ursula. She's read the Arcanum. Okay, so there's like 1700 plus years where the Europeans didn't have this understanding of how to get porcelain. Okay. Now they had high temperature, they had salt-fired stoneware, but even that was relatively new invention. But that they came to this place where what they did is that they have an entire culture, an entire aesthetic culture, whether it's soft paste porcelain or Maiolica or Delft or faience or any of these things that were meant just to fake Chinese ware, the refinement and whiteness of Chinese ware. And so how they were doing it was they were using lead because they didn't have high temperature as an option. So they were faking it till they made it. And so coming back to the question about why do I make a big deal of the temperature and the cones and all this? Because at cone 10 is really the only place where this happens. We'll get into cone 6 in a few lectures of what is really going on at cone 6. But the short answer is you can't get feldspar and clay and quartz and alkaline earth to melt at cone 6. Okay, and have it be a high quality glaze. And I'll show you something. Hold on real quick. That's not what I wanted. Let me just open up. Okay. Move this over here and do a screen share. So why is this the case? Okay. Again, this will come up in the next lecture after the break. Okay, here's my glaze calculator. If I take NephSi, which is my most concentrated alkaline earth source, alkali metal source, and whiting, I just happen to know if I do the 66.6 NephSi, 33.3 whiting. Okay? So, NephSi and whiting. Now, there's no clay, there's no flint in any of this. I get my 0.3 to 0.7 ratio, right? 0.3 to 0.7, so it's a well-balanced glaze, and we'll talk about later exactly why we need the 0.3 to 0.7, but this is rather important. Okay, so I've got a balanced flux ratio, which is good. I want to see that. But my alumina level is automatically 0.3. My silica level is 1.43, which puts me, well, I can scroll down, which puts me right here on Stull. Okay? And that's at cone 10. So basically, then as soon as I add, let's just say I add the 10% clay to keep this glaze suspended. 10% clay to keep this suspended, my alumina level jumps up to 0.37. So now I am here, okay? This is the absolute minimum of a glaze I can make, the lowest amounts of silica and alumina, and it will just melt at cone 10, but not under that, because that's what the cones teach us. Because remember, cone 10, right, is when a composition is starting to soften. But it takes 6 to 8 cones for it to go from softening to melting, 100 degrees C. Okay, so now again hold on, I got a bunch of things open here. So when we come to the cone chart here, right? This is literally how our cones fall on Stull. Okay, cone 1 is here, cone 2 is here. Like I said, the actual compositions of cones are on the map. So cone 4, right, is actually a cone 10 glaze when it's starting to soften. Okay, so what that means is that, now I know this sounds a little bit weird, and it's probably everybody's like scratching their heads of what the hell are you saying? What this means is that the composition of cone 4, okay, is fully melted at cone 10. Okay, so this literal composition is soft at cone 4, but it is melted 6 cones hotter, which would be cone 10. Okay, so why is this cone 4? Because this composition will be soft at cone 4, but will melt 6 cones later, which is cone 10. Does that make sense? I see a lot of stunned silence. Also a lot of muted microphones.
So you're talking, make the distinction, what does soften mean versus melted?
So why is that important?
Yeah.
It's
I mean, when you
best-
say soften, what's that define?
So they can melt.
Okay, so this
Does
is
it mean it bends then?
it bends.
Okay, but still, I guess it's the same question as what Ursula, why such an emphasis on that? I'm not trying to be rude. I sound rude.
No.
Sorry.
No. It's
I guess
absolutely
I'm still not understanding.
okay. No, it's absolutely fine. Because remember, cones are based on the material not melting, but softening, beginning to melt.
Okay.
If we were judging a cone based on it being completely melted, it does us no good. It's a puddle. So what the cone compositions are telling us is this composition, this specific chemistry, is beginning to melt.
Oh, okay.
Okay. But what that means is 6 cones later, 6 cones hotter, that exact same composition is melted. Okay. Means at cone, say we'll just say that this is the cone beginning to soften. Okay. These particles here are starting to melt. Okay. They've gone from rough and undefined to they're starting to connect and form a melting mass. Okay. As the temperature climbs, it melts more until it's completely melted.
Okay.
But when we are tracking a cone, when our cone has bent to 3 o'clock, it is at this point. It is beginning to melt. It is softening, but it is not melted. Okay. But 6 cones hotter, it is melted. And what that means is this. Oops. Oh, too big. Hold on. Over here. So this, and again, it's hard to see because it's just white on white, but this is cone 4 crushed up and applied as a glaze and fired to cone 10. Because if you fired a cone 4 to cone 4, which is, hold on, sorry, I got to pull up my temperature chart because even I don't remember. Cone 4 is, oh, stop. Okay, so cone 4 is 1183. Okay, C, right? So this composition softens at 1183, but it melts at 1305.
Can I ask a question?
Mm-hmm.
I might not be understanding why the lack of understanding. To me, are you saying just the composition of the different cones is a way that we can just look simply at glaze chemistry because the cones are made up of glazes and each cone is made up of different ingredients? So in a way, we just have an example of what's actually going on in our glazes by just looking at the cones, right? I mean,
Well, it's not the different ingredients. It's minor changes in the chemistry of the cones.
Okay, but so each cone 4, cone 5, cone 6, they're made up of different, well, it's different chemistry, different ingredients though, right?
Different proportions.
Proportions, okay. So we're focusing on the cones to show us what happens to a glaze, right?
Right.
Okay.
Because.
So that's why we're emphasizing that.
Denise, were you going to say something?
I was going to say, I think that's why this lecture is so important and how far you get into it, because what I understood with the cones from where I was is that the idea that molecular unity and the way these ratios are, and then how you can apply it to that Sager chart, because you have the cone part in it too, and there are these, you start to see these patterns with the ratio of alumina and silica to the fluxes, and then how that then translates to that other chart that you mentioned. Is that, am I on track with that? That's how I see the cones relating to that because of all the ratios, and then that second chart.
Yes, and it helps. Part of this is not everybody's up to the same point, but let me show you this. 30, 40, 50, 60, 60, 90, We'll just call it that. Okay. So this formula that I've got up on the screen right here, okay, this is the formula for cone 4. Okay, you could literally mix this up and make your own cone 4. Okay, 30% NFSI, 15% whiting, 12.6% EPK, and 42% flint. Okay. And why that's important is because it's got a position on the map. Because if you fire this to cone 4, okay, that indicates the temperature of cone 4. If you fire this to cone 10, it is fully melted. It goes from just being an indicator of temperature to a glaze. So what we're doing is under firing glazes to indicate temperature.
Yeah.
Okay. Now I can do the same thing. If I can come in and I can tweak this formula and I can take this up to 40, 41, take this up to 10. Okay. So now all I did was increase the silica and alumina. Okay. And now this is the formula for cone. Actually, I'm sorry. The last one was cone 5. This is cone 6. Okay. 0.6 alumina, 6 silica, 10-to-1 silica to alumina ratio. Okay. So what I have done is I have now taken a different composition and increased the melting temperature of this composition. Okay. By just adding silica and alumina. I didn't touch the fluxes to make this change. I added clay to bring in alumina and flint to bring in silica. And this composition now melts a cone higher than the previous composition, but it's still on the map. Okay, if I come down here, it's gone from here on the map to here. Okay, and so you can travel down, and that's what this is doing by saying different levels of silica and alumina reflect different temperatures. Okay, and this is one of those confusing things because this is that abstract thought where we all say, oh, cone 10 is cone 10. But what I'm here to tell you is cone 10 is a myth. There is no spoon. Right? That it's all about what is the relationship between silica, alumina, and fluxes in your glaze?
Okay, so Matt, when you just did that changing,
yep,
it before you had a perfect 10-to-1 silica alumina ratio. When you just changed it to cone, it went to 9.98.
Right.
In my mind, it would have been, so basically it would have, like, that's not a very big change, right? Like, I thought, I guess in my mind, I would think it would be like, it would go like 9-to-1 or something. I mean, something more dramatic than just like a 2/100ths of a change in the ratio.
Well, the thing is that I didn't change the ratio, but I did change the actual amounts. Okay? Because if you come back and look, that I went from I added a complete mole of silica and 0.1 moles of alumina, of actual silica and alumina, an entire mole more. Okay, so talking about how a mole is a specific number of atoms, I added that many more atoms to this composition. And what that did is that it increased the melting temperature by 1 cone.
But it didn't change the ratio significant between the silica and the aluminum, right?
I adjusted to make sure I got the same ratio because that's how cones work. All the cones have a 10-to-1 silica to alumina ratio. By keeping that ratio the same, we're keeping the melting performance the same.
So and maybe this is a misunderstanding. So I guess I always thought that the ratio of silica to alumina, I guess it's because, like, can I say this, and if it's totally wrong, you can
go for it.
All right. So if you have cone like if you were to look at those things at cone 10, right? To me, in my mind, it would logically make sense that the silica alumina ratio, as you went up in cones, would change so that the ratio would get smaller. So it'd be almost like more like like moving towards a matte glaze ratio, right? So you would get smaller if you're looking at them in relation to cone 10. Does that make sense?
Yeah, but that's not what the curve says. Because if you keep it at 10-to-1 ratio, you're going to move along that curve.
Right. Okay. So, okay. I think I've got where your question's coming in. Hold on.
I don't know. I'm not saying it well.
No. Okay. So again, I don't know how far into the lecture you've gotten. And again, that this is a little scattershot.
I had 53 minutes left. 53
Okay.
minutes left.
I don't think you've gotten to this yet. With 53
No, I didn't get to
minutes
that.
left.
I didn't get to that.
Okay. So now remember, the thing about the map here is that this goes from 0 silica and alumina, or 0 silica up. This goes from 0 alumina up. So this is literally nothing. Okay. This is 0. As you increase, okay, you have all the different ratios under the sun, depending on where the chemistry of your glaze falls. And remember, the thing that you have to note, and again, I'm sorry if you haven't watched the class and you just think I'm speaking gobbledygook, but every single point on this map has exactly the same amount of fluxes. Okay, hold that into your head.
Okay.
Every single point has exactly the same amount of fluxes. That's the way glazes work. That's the way we look at them, okay, in a systematic manner. So we can go from 0, we just say go from 0 silica to some silica. It doesn't even matter what the number is. From less to more. Same with the new alumina. We go from 0, less, all the way up to more. Now, you can have different ratios. Okay? Because, and again, let's just make this 40, 20, 30, 10, okay? If I plug 4, 3, 2, 1 into here, oh no, I've got this backwards, sorry. That should be 10, that's 30. Okay, so just plug the 4, 3, 2, 1 glaze, right? So now 4, 3, 2, 1 has an 8-to-1 silica to alumina ratio, but still got the exact same amount of fluxes, okay? But it's now fallen off the cone chart because the cones are constricted to 10-to-1. That's how we keep the temperature chemistry regular, is by patting kittens' butts.
Huh?
Sorry, Kate just picked up a kitten and started patting its butt, so I thought no. She turned red. I've been talking about you behind your back. I've been talking to Stephanie Burke about you.
Baby monitor. That's what she said that you really recommended those. Yeah.
Hold on. I'm Kate. I'm sorry. I just noticed your question. I'll have to get back to it in a second. Kate Smith. So the ratios, when we start to talk about glazes, now become a variable. But when we're talking about cones, cones are static in their silica to alumina ratio, but they change their amount. Okay, so this becomes a very important concept when talking about the map, because we now can think about temperature is a range. Okay, because although this is literally, cone 4 is literally right here, right? And cone 5 is literally right here, but there's a range where melted is okay. Okay, where you'll get a whole bunch of different compositions that will melt, but it really depends on temperature, what you're firing to and what your composition is, and what is the relationship between those two. I see so much head scratching. It's sort of great.
Matt, when you were showing the different sections of what happens, like when crazing happens and when this or that, under fire, lower fire, and then you had that one where you made your own and you had that white spot and you said that this was your marking.
Right.
It seemed like in that I was trying to figure out what the cutoff areas were, because it seemed to be like in some of those areas, they were in ones that were either, it seemed like it was going out of bounds for some reason. Thinking back and not looking at this, but something about, if you explain it more to me, to us.
Can you say that again?
Well, if you would just go over that part where, you were talking about the different ranges of that chart, and then you said, and then you had a line that you showed us that you created yourself. You said, this wasn't part of someone else's, this was mine. And
could you guys see me on the screen share?
No, I see the image.
Or yeah, I mean, you see my map here with the purple and yellow areas. Sorry, Phil and Kate say they're not getting my screen share. They're just, you do see the screen share. Okay. Okay. So what I'm basically saying here is actually, this is a great question, because temperature is a range. Okay. Cones are showing us that as you increase the actual amounts of silicon alumina, not the ratio, but the actual amounts, that temperature increases. Okay. So, we'll just say this isn't exactly right, but we'll say cone 1, cone 2, cone 3, cone 4, et cetera, et cetera. Does that make sense to everybody?
Mm-hmm.
Okay. Well, what that means is Stull, the whole map, only applies to cone 10. Okay. So instead of having a range of temperatures, this is everything fired at this temperature, at one set temperature. And what that means is as you increase physical amounts of silicon alumina, at some point you're going to get a cutoff where it will stop melting at cone 10. And that's what this yellow line here, okay, is what I'm indicating. That glazes over this area, so shaded in purple here, will not melt because there is physically too much silica and alumina to melt at this temperature. So we go back to the car metaphor of the tiny car will move really far on 1 gallon of gas. The big truck will move less far on 1 gallon of gas. Well, imagine instead you're trying to move a cruise liner. Okay, a big giant ship that weighs thousands of pounds. And you may have heard, like, those ships burn like 1 gallon of fuel to move 1 foot. Okay, so by adding more silicon alumina, it just will not melt at cone 10.
So now going to that, okay, this is perfect then. So when I'm looking at that, because you're showing underfired, overfired, and then in that situation using that particular clay body, crazing happens.
Mm-hmm.
The ideal clay bodies within something being glossy, semi-matte, or matte, with being able to use those cones would be everything in that white area then?
Well, it's not just the white area. It's everything under, again, it's a little bit, I know it's a little bit confusing. I can just do this. Okay. If I remove that, it's everything under this yellow arch.
Okay.
Okay. So the thing I just deleted were glazes that you can't make because feldspar adds too much silicon alumina. So literally you just cannot make these. You physically can't make them with our materials because because feldspar is 1 flux, 1 alumina, 6 silica. It just automatically has too much silica. And actually we just looked at that. If I come back to this and just do this again, right? If I do 66.6 and 33.3, okay? So with just feldspar and whiting, I automatically hit, come down here, this point. That's as low of a point on Stull as you can create using feldspar and whiting. Okay? And that's really important because basically it means all this you can't make, all this you can't make. So that's why I just had that box and deleted it. Okay. So coming back to here. So everything under this will melt, will form a real glaze. Okay. But when you get over it, there is physically too much material to melt. Okay. Now, if you could fire to a hotter cone, you could put glazes up here. Okay, but at cone 10, you cannot get these to melt. And this, again, is an incredibly important concept, because what this is saying is, okay, with using, again, feldspar, alkali metal, or I'm sorry, alkali earth, clay, and quartz, right, which are the 4 materials we need to make a glaze. We talked about that, excuse me, very early on. Okay, you need the 2 fluxes to get the melting going, and you need silica and alumina to make your glaze. So you have to use those 4 materials. When you put those in, okay, you automatically get this point, which is what we just looked at. Oh, I'm sorry, I'm on the wrong. You get this point here, right? So it means that everything above this are real glazes. Okay, but you cannot get under that. And that's so important, because what that is saying again is, with those 4 materials, you cannot make glazes under cone 10. And that's why bringing up the materials and the cones to Ursula's original question are so important, because materials relate to compositions, relate to temperature. That's why I go back to the cones so much, because the cones, again, are just specific chemical compositions, and they are our glazes. Oh, I see the headaches brewing. And I know you guys are like hating me right now, but I love this. This is why I wanted to get to this class, to go to the break, because you guys are going to now spend a month scratching your heads and being angry at me, and then you're going to eureka this shit, and your minds are going to be blown.
I have a question.
Okay.
Now, I understood it one way, and then as you started it, I got like, oh dear, and then okay. So, and I can't point, but at the screen.
Yep.
So you're saying you can keep that silica alumina the same ratio, but keep increasing, and at this curve up here, the 10, they're simply, the fluxes it's so saturated with the silica alumina, it does not melt, can't melt, right? Mm-hmm. But I get that.
Okay.
And then there was something that Ursula, when you said that these are real glazes, but what is that I guess was, I just wanted to, do I understand that? But if you were to increase flux, change flux, go to a boron, and doesn't that have an impact on the low temp, the mid range, and the high range? Isn't there a whole way of understanding that too, or isn't that we're only dealing with?
Don't start thinking about that yet.
Oh, okay.
We will get there.
I take orders very well. Good. Okay. So, but what you were really trying to say is we can keep this silica in proportion, and that we can keep increasing it, and that gets this zooming thing with the cones, right? Mm-hmm. Charting. And then they're just basically, the gasoline will say for the big barge, that's the fluxes that cannot get that to do it anymore. There's a certain point where they won't do their job. They're done. They're spent.
Right. Well, it's that, yeah.
Is that what you?
There's too much physical material to melt. Okay. That the fluxes cannot do it unless you increase the heat, the temperature.
Okay. All right.
Okay, because remember, it's not just the fluxes and the silica and alumina. It's fluxes, silica and alumina, and heat.
Okay.
Okay, which is why we come back to this thing of, why is cone 10 cone 10? Because when you take those 4 materials, and again, that's sort of what I'm doing right here. Okay, we have, oops, wrong one.
Yeah, I can't see it. I'm going to mute myself. Sorry, I talked too much.
No, you're fine. Again, we have 4 materials to make up a glaze, right? Everybody comfortable with that? We'll use nepheline cyanide for our feldspar, alkaline earth in the form of whiting, clay, and flint. Okay. So first thing that we need to do is we've got our 2 fluxes. Nephci brings our alkaline metal. Whiting brings in our alkaline earth. So we need to get it to a 0.3 to 0.7 ratio. So that's giving us the proper balance between the two different fluxes. Okay. And we will talk extensively about why we are at 0.3 to 0.7. Okay. As we go. But for now, take it as given. You need to see a 0.3 to 0.7. Basically, otherwise your glaze will fall apart. Okay. So as soon as you take these two materials and make them a 0.3 to 0.7, well, the NEFSI has silica and alumina inside of it. Okay. So if we balance 0.3 to 0.7, that automatically gives us an alumina level of 0.3 and a silica level of 1.43. Okay. Now, if you take the map as a given, right, you take Stull's map and say, this is every glaze fired at cone 10. But this is, and we have to have these four materials to make a glaze. That this is literally the lowest amount of silica and alumina that we can have. All right. And we have to have silicon alumina to make a glass. And then the next jump is with the cones. Basically, we're adding more and more silicon alumina to get to pure silica and alumina, which have a very high melting temperature. So as we add them, if every cone has exactly the same amount of flux, we're just getting more and more silicon alumina closer to pure silicon alumina, which reflects a higher temperature. Pure silica melts at 1700 degrees. Okay, so as you add it, you're getting closer to that pure silica, and so you need higher temperatures to melt that glaze. It's a glaze. Okay, it's a glass. And so we're doing the same thing, but we're just keeping constrained to what melts at cone 10. If you say these materials need cone 10 to melt, and then what else will melt at cone 10? What I am saying is basically everything under this arch in the map will melt at cone 10. Okay. Over here is pretty simple. There's just too much silica. This is the high silica corner of the map. Okay. Too much silica to melt at all. Up here, same problem. Too much alumina to melt. Okay. Through here.
But you would get the softening there up in that corner.
Yep.
I mean, you wouldn't
absolutely.
get a melt. You just get the softening at cone 10 or whatever that up in the corner.
Yep.
Okay.
And as we talk about matte glazes, these will look like matte glazes, but they are actually just under fired. Okay. Whereas these are true matte glazes, which are crystals growing in the glass. Okay. And so too much silica, too much aluminum, too much of both to melt at cone 10. If you fired to cone 11, these would start to melt. If you fired to cone 11, these would start to melt. If you fired to cone 12, these would start to melt. If you fired to cone 13, these would start to melt. And this map actually would go on into outer space. Okay, it just keep going on, and you'd get cone 14, cone 15, cone 16, and now I've run out of screen room. Okay, because with the same amount of flux, by adding silicon alumina, you have to add temperature. But we're not doing that. We're just saying cone 10 is our temperature. So what will melt at cone 10? These will melt at cone 10. But don't even worry about it, because when you start plugging in glazes, again, you come back to 40, 20, and 30. You come back to 4, 3, 2, 1. Right? So 4, 3, 2, 1. Again, now, literally, this is just an old tried and true recipe, and 4, 3, 2, 1 will come up plenty of times. 0.3 to 0.7. I had nothing to do with that. That's just what people know, or what's a quality glaze, right? And hey, look, the silica and alumina levels are right in the middle. Again, that arch would be right about up here. Okay, but the silicon alumina level right in the melting zone. 4, 3, 2, 1 is a perfect cone 10 gloss, and shockingly enough, the map tells us it'll be a perfect cone 10 gloss. magic, science. Again, I see a lot of questions, and I think I'm going to cut you guys off. I will answer as many questions as you have, but I see the gears turning. I see some light puffs of smoke coming from people's ears, and I see skepticism, which I like. Yeah, Kate's about to get gum in her hair. Or in her cat's fur. Ursula, do you have a question?
No, I'm sorry. I think the thing that I think that I don't even know what to say. I think that just as that what you just said, that basically, like, so each of these cones basically, like if you take cone 6, it would really be melting at cone, with that it would be melting at cone 12, let's just say, okay? Like it would be, like you said with cone 4, let's just say cone 6 would be melted at 12, and it's just because I think that what made sense to me, I think, and what you just said, was that you're shooting for alumina and silica to be melting without the flux. And I mean, not you're shooting for it, but that's where you're heading, right? And so then there's proportionally the lesser amount of flux. And because we're just looking at it at cone 10, that's, so basically what, when you're talking about the cones, okay, I'm saying this terribly. When you're talking about the cones, basically they're proportionally getting higher at their melting temperature.
Yes.
If eventually, which is, I guess, what we know about cones, but for some reason,
that is the nature of cones. You're exactly
right.
Each cone is a higher temperature.
No, but I mean, like in terms of you're talking about like how they're going to eventually totally melt. But I think to me, it makes the part that seemed like it makes sense is the idea that the amount of flux is being
reduced.
Reduced.
Don't think of it that way. Actually, I don't want you to think of it that way.
Okay, sorry.
The amount of flux stays exactly the same.
But the amount of silica and alumina...
But the proportion is less.
I don't even want to say that. The amount of flux stays exactly the same. The amount of silica and alumina goes up in a systematic way in each cone.
Yeah.
Okay, so you can go back and look at the chart, but literally we'll just say cone 1 is 1 flux, 1 silica. Cone 2 is 1 flux, 2 silica. Cone 3 is 1 flux, 3 silica. Cone 4 is 1 flux, 4 silica. That's a massively gross simplification, but theoretically that is actually what is happening. Because when we come back to the compositions, oops, I turned off my screen share. Okay. Cone 5 is literally 1 flux. Add these together. That's 1 flux, 5 silica. Cone 6 is 1 flux, 6 silica. Okay. And yes, we're also systematically adding alumina, but it is literally that step. Okay. 1 flux, blank silica. 1 flux, blank plus 1, moving upwards. And that is increasing the melting temperature. Okay, but coming back to glazes, coming back to the map is saying we're not looking at every temperature. We're looking at this temperature. And we're not looking at just this many silica for this many alumina. We're looking at all the variations of silica to alumina. But every point has the 1 flux.
But isn't that map based on cone 11? I mean, I guess that doesn't really matter.
That's a relativism, but yes, technically cone 11.
So Matt, the map, the fluxes are constant, the cone is constant, and the only thing changing is the alumina and silica.
Exactly.
So then if you were to look at and then you're saying that everything, this is what you can do at cone 10. And I'm thinking later on, then when you go to cone 6 and stuff, are you doing different maps? Or is there are you modifying it in a different way so that you can look at different temperatures where you're firing at? with these glazes?
Hold on, wait, I'm gonna stop this. You can see my shit-eating grin. Yeah. Yes.
Or am I completely confused?
No, you're exactly right. Okay. The amazing thing is that at other temperatures, the map is the same. At cone 6, at cone 04, you get the same map. But you have to add the right things to get the map to work. That's where we're going.
So then we're changing a constant.
We're adding in a new constant.
Adding in a constant. Okay.
And that constant is boron.
Okay, I get it. Okay.
Boron!
I was going to say, is there some like secret word now that we have to exchange so we're in this understanding group? Like, are we kind of like the fraternity? Have we gone through the hazing yet? Or are we still
gone through,
we're in the process?
I haven't even finished hazing you. You still think you like me. You still show up here. You don't dread me yet, but I will show you one thing.
We're missing one person. Who are we missing? Oh, Phil.
Phil's there with Kate.
Phil's sharing.
No, it's okay. Everyone's here. So they didn't lose
consolidated.
anyone. They're all showing up.
No one. Yeah, I know. No one's run away yet. This little rainbow in front of you, aside from my children, is the single greatest creation of my life. Now, I don't wanna to toot my own horn, but I had a guy emailing me from Croatia a few weeks ago who was telling me that the list should be Seeger, Stull, Cats because of this map. And I'm not saying he's not wrong, because what this map.
I just want to say, my 13-year-old just looked in and was like, because I'm like having fun doing this stuff, and she thinks we're like the biggest dorks. I just want to tell you.
We are totally dorks. I know. We can't be cool to teens.
This just looks like the California coastline.
It does look like the California coastline, but it's even better.
I live in Minnesota. California looks pretty good right now, so
Sure, it's very snowy up there.
Mm-hmm.
What this map tells you is exactly how much boron you have to add to a glaze to get the map to recreate itself at any temperature. Okay? So again, we have to come back to, you can't make a glaze with feldspar, carbonate, clay, and quartz under cone 10. That is durable. You can't. Okay, go ahead.
Right. Your statement about cone 10 is actually, we call it high fire, but it's actually low because it is the lowest temperature that you can fire and get maturity with the ratio of the earth. Okay, the earth and metals and of one that make one, and that the ratio of silica and alumina remain the same.
Hey, Kate, can I tell you something?
No.
You just blew my mind. Because I have never thought of it that way, but you're absolutely correct.
Can you repeat that, Kate?
No.
I was thinking of...
Okay, so what Matt said was that cone 10 is that, though we call it a high fire number, it is actually the lowest temperature that you can get this ratio of alumina and silica with the, this is where I'm messing up the earths and the metals.
That's fine. You're on the right path.
Alkaline metals to equal 1. They have to equal 1, right?
Mm-hmm.
And then the ratio of the silica and the alumina remain the same. And that makes it cone 10. I told you I couldn't say it again. So that your constant is cone 10. That you're always so blah 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 blah. I'm sorry, I can't say it anymore.
No. You're exactly right. What Kate is saying is that we call this high temperature. We call cone 10 high temperature. It's actually low temperature when you're thinking about silica and fluxes.
Okay.
High five,
Okay.
Kate. Shall high five you.
Oh, nice high five. Hey, I like that.
High five.
Hey,
Then after you get to cone 10 with just the alkali metals, then you can add flux to decrease to lower cones, and your flux is on, and that's where your wonderful graph comes in.
except that boron is not a flux.
What is boron?
It is a glass former that melts at a lower temperature.
Okay.
But hold that thought, because literally it's going to be a couple of weeks after the break, but I have an entire lecture just on boron. But to go back, okay, again, this is the incredibly important thing. Why is cone 10 cone 10? Why does cone 6 piss me off so much? Okay. Now we've got two conditions. Another cat butt. There's a lot of cat butt in this video. Okay, wait. Why is cone 10 cone 10? Why do we have this arbitrary number? Okay. Because first, when we go to clay bodies, cone 10 is when mullite formation is complete. And I know we haven't talked about clay a lot, but that came up earlier. Mullite is the bones in our clay body, muscles and bones. Mullite formation is complete at cone 10. Number 1. Then the amazing thing, and I'm a dyed-in-the-wool obnoxious atheist, but sometimes you go, nature is amazing, because cone 10 is also exactly the same temperature at which feldspar, alkaline earth, clay, and quartz come together to make a glaze that will melt. That is why cone 10 is cone 10. Or I should say, make a glaze that will melt that is of high quality. Okay, this is the big deal. This is why Stull matters. This is why the cones matter. This is why cone 10 matters. So, everything else under cone 10 is a bastardization of that chemistry. You smirking at my terminology, Ursula? I see all of your faces. Bastard glazes. But that doesn't mean that they're bad. In fact, the amazing thing that we will learn is that you can work at all of those temperatures and, in fact, make even better glazes. Okay, that's what's so cool.
I have a question.
I have an answer.
I have a memory of Cardi making a comment that because of something, you can actually make an incredibly durable, like 04 or something like that. Is this true or not?
Yeah, that's my research.
Ah, excellent. Okay.
Here's the deal.
That's your research?
That's my research.
Damn. Talking to the man. Okay. I didn't know you were that guy. Okay.
I'm that guy. I'm the boron guy. That's why that thing I showed you is what I'm so proud of. Because a glaze at cone 04 that follows the guidelines that I'm laying out here of the UMF plus boron, which is what we need to get the temperature to melt at cone 04, is actually stronger than an equivalent glaze at cone 10 without boron. And the cone 10 glaze is incredible. At cone 04, it's even better. And we'll get to all that. Okay? But first we have to focus on coming back to cone 10. So I do want to talk about, I do want to just bring it back to this. Okay, just to make sure, because now I see the lights clicking. I see people, we're here. It's late, but, everybody's in bed at my house. So, I can do this. But again, I just want everybody to feel comfortable, to understand why we're dealing with cone 10. Because now I can put it, now watch this. Let's just start with just NEFSI. Okay. Now this says 40, but remember, this is normalizing it to 100. Okay. So if I have 100% NEFSI, okay, what do I get? I get all alkali metals, 0.97 alkali metals, 0.3 alkaline earths. Okay. Because there's some trace calcium in NEFSI. That's fine. Okay. I get 0.99 aluminum, 4.69 silica. Okay, that doesn't even matter. But I've got all alkali metal. Now, as soon as I add in the alkali earth, okay, and again, now I just plugged in the number because I know what works. But, I got my 0.3 to 0.7. Now, you can make different ratios. I can make this 10. Okay. Now, do I have a different flux ratio here? Yes, but I do not want that. This is a glaze that is physically weak, okay, which means it will break down. So the dreaded food-safe glazes, durable glazes, okay, the way to combat that is 0.3 to 0.7. 0.3 to 0.7 glazes are the strongest and the best to stand up against the abuse of food, dishwashers, acids, soaps, all that kind of stuff. And we'll get into all this later. So, take your notes, but don't worry about it. We will talk about this extensively. So you want 0.3 to 0.7.
So you can eyeball some glaze formulas and tell whether or not they're going to work. Because before you were saying you couldn't, but you really can if you are familiar with those ratios, right?
Did I say you couldn't?
I don't know what you're talking about. At one point you were saying, but when you looked at something, you couldn't tell what was going to happen to it, but you really can, it sounds like.
Oh yeah, I can. You'll be able to too. That's the magic of the UMF, because compositions translate to the map. Okay? I mean, here, well, let's just do this real quick. Oh wait, that's my Hangout. Here, I'll open a new browser so I don't screw that up. Okay, let's go. Let me move this onto my screen share and we'll go to Glazy. Hi, Glazy. Oh, look. This lady's been uploading today. I don't want to look at her glazes. I want to find... This will come up in a later lecture. I actually stole this one. Where did he put it? It doesn't even matter. I could literally click on anything here. This one. Okay. Honey Gold. I've been looking at this one recently. Real sexy glaze. Okay. Whatever. Here's the formula. Don't care. Okay. Let me only go so far so everybody can see this. Here's the UMF breakdown. Okay. I don't even care what the formula is. Basically 0.3 to 0.7. Okay. Not literally, but pretty close. And we'll get into all this later. This one happens to have a 10 to 1 silica to alumina ratio. Fine. But the thing that's amazing, okay, is you come down to Glazy, and what it does is that it automatically plots it on stall. And the chemistry equals the map. That's what's so important. Okay. So, as to Denise's question, can I look at chemistry and automatically tell what it's going to do? Yeah, because I have the map memorized in my head. I know what the numbers will translate to the map. And, are you guys going to be able to do that right away? No, but I've been doing this for 20 years. Like, I stare at this map all day long, every day. Like, this is just what I do. I don't have much of a life. My children aren't very good with conversation. Although you guys want to see the cutest? Here, hold on. Wait. Here. Since my parents just posted this on Facebook. Let's see, where is it? Isn't it terrible when you share a text message with your parents and then they post it? They post the personal images you sent on Facebook. Where is it? Brag about my cute kids. Come on, where'd she put it? Where'd she put it? If you guys had to listen to me talk, you can. Oh, there it is.
Oh, cute.
That's my son tonight. Before his concert, he's 5. That's Eli.
He's adorable.
Yeah, he asked for the bow tie.
So, for your clay classes, are there maps like this too? Like, is this like things like? I'm just curious. Is this like for your glaze classes, or do you have tricks of the trade like this? Or,
I have a lot of tricks for clays, but I will tell you the most. One of my dedicated students, who's a wonderful man, got through my clays class, and he got to the very end, and he's like, "Well, where's the magic answer?" And I'm like, "No magic answer." And he's like, "But there's a magic answer for glazes," and I'm like, "Yeah, that was glazes." Clays are close. There's a lot of predictive ability that we have for clays, but it's not there yet. But it's close.
So do you teach the clay class first generally, and then the glaze class?
No, the clays class I generally teach second. For 2 main reasons. The clays class is generally not as much interest because most people don't make their own clays. Most people buy commercial clays, and if you're not mixing your clay, I was just debating with somebody today because I have a clays class that starts next week, and I don't know if it'll run. The enrollment's pretty low because if people are mixing their own clay, why do they want to learn about clay formulas? And I was sort of debating with someone who is enrolled, who's taken. Actually, I was talking with Farad, because she wants to take the clays class that starts next week, and I was saying, maybe I should remake it into a firings class, because it is a lot about clays, is about firings, but that's just a conceptual problem. But the catch with clays is there's no easy answer. Clays are. Cardi thinks he's figured out a map, but it's not perfect. It needs a lot of work. It's close, but it's not there yet. But with the glazes, the map works. And I don't remember. Did I get to the part in the lectures where I slander glaze limits? Or did I? No, actually, I think I left it out of. I think I left it out of this class altogether.
No, you slandered glaze limits. You
yeah.
did.
Okay. Good. Yeah, because glaze limits are garbage.
You said to forget everything about glaze limits.
Right. Because that's my boron lecture. I'm giving you guys extra information. Yeah, limits are a nightmare because limits place fake restrictions on your glaze compositions. But what the map tells us, I really like the map concept because A, it gives us a visual resource, which I think for people in the arts community is super important. But B, it tells us that even when I draw that curved line, right? This line is still just my interpretation. That's not a hard and fast line. There is flexibility as to exactly what will work. But really, at the end of the day, your cone 10 glazes are going to fall sort of right in about here. Okay? Now, here's the scary thing. Every cone 10 glaze out there, with a few exceptions for some special effect glazes, falls within this tiny, tiny little region. Okay? And that's the crazy thing, that there's actually minor amounts of variation that make up all these different glazes. So why do we have all these different glazes? Well, A, there's a lot of change that can go on within this area. There's a lot of effect you can get from changing colorants, from changing fluxes, okay? Because we talk about sodium and calcium, but what about lithium and barium? What's that going to do? What are those going to do with a lot of iron? What are those going to do with cobalt? What are those going to do with chrome in with zinc or with copper and reduction, that's where all the variation starts to come in. But the base of the glaze is inherently similar for all glazes. So it really comes down into the subtlety of understanding. So really, sort of at this point, as we're finishing up with this point in the discussion and this point in the class, that's why, I really wanted to make sure we get to this point when we go on break of start to go and look at glazes, poke around glazy and look at the numbers. Get through this lecture first if you haven't. Okay, get through this lecture 2 or 3 or 6 times. We're all joking, except I'm serious. But get through it, and then take the glazes that you're working with in the lab and start to plug them in. Just go to Glazy and just start pulling up formulas and start to see how those numbers translate to a result. Okay. Now, the one thing I would say is, although I know everybody's working at lots of different temperatures, right now try to stick to cone 10. Because as soon as boron comes in, as soon as we start talking about lower temperatures, you're going to start to get more confused. And this and that. So stick to cone 10 and just poke around. Okay. Now I see a lot of sleepyheads. Dawn's taken off her glasses. She can't keep her eyes open. Robin's really trying to look like she's still awake, but it's okay. I know. Peter's got to stay on his elbows, and Phil, I think, is probably asleep on the couch. Oh, there he is. Hey. But are there any other questions at this point, or have I left you all stunned like a deer in the headlights?
Exhausted.
No, make it stop. Make it stop.
Oh my
I can
God.
talk all night.
I understood it better when I finished listening to your lecture.
Good.
Now I'm more confused. No, it's good. It's all good.
Like I said, this is a perfect point to stop because you do need to digest this content. Because I will not deny that the rest of the course, and specifically the next 1, 2, 3, 4 lectures at least when we get back, the first 4 are pounding this into the ground. What we do, how we do. Like how it all works. Whoa, I can hear myself. Okay. No, I'm freaking out. I'm going to stop talking now because I hear myself. Oh, good. It went away. Next hangout. I haven't even looked at the calendar. So the next class goes up Monday, the 9th of January, I think, unless I've got that calendar wrong. Ursula's the authority. So what I would probably say is we can aim for the 11th, because even though there'll only be 1 new class, I suspect you guys will have a lot of questions about just this after having thought about it and looked at glazes and poked around, unless you all just run away and, run like with your, screaming that you don't want to think about this for the rest of your holiday. But right now I will tentatively say Wednesday, the 11th. Which would be good because the week after is not good for me. Yeah. So I forget how long, so this is 7. There are 13 lectures. So there are 6 more lectures to come after this. So it goes into the 2nd week of February with lectures. So get the 2nd lab done, get that fired and documented over the break. And posted. We'll talk about that when we come back. There'll be a new lab when we come back. Everybody go. Enjoy your holidays on ice. Tip back a few. Don't drive. Don't do anything I would do. Like try to keep a 5-year-old up till midnight on New Year's.
If you set the clock back to 10 o'clock, it looks like 12 o'clock, you can get your kids to bed earlier with excitement at midnight.
You want to know the most evil thing that goes on now? Netflix has a countdown show.
Hmm.
So you just put it on whenever. As soon as it's dark, you just put on Netflix countdown, and it's like 7:30, and you're like, oh my God, it's midnight. Oh, 10, 9, 8, go to bed.
What was your son's concert?
Oh, it's just, it was the holiday concert. So he sang Dreidel and a Puerto Rican song I didn't know and Jingle Bell Rock. And, it was the kindergartners through the first graders. So he was very excited.
Cool.
It was very cute.
Yeah, it was very cute. So let's see. May we get any lectures ahead of time? No.
I can't keep up as it is. However, if I have a couple of weeks off, I was thinking if you already have pre-recorded and released them. That's all. Just a question.
No, because I don't want to enable. I know that some people like you are have their pace, but I also know that the compulsive people will try to eat everything at once.
Oh, okay.
So I'll keep it. Take this and digest and go and look at glazes and play around. I want you to think about what you've done by inviting me into your homes and your heads, because even if you just think I'm full of it right now, like I said, like you're going to be like sipping a mimosa Christmas morning and you're going to be like, oh my God, Matt and my parents were so right. You should have listened.
I was gonna say I talked to Audra, and she's gonna make us a little place back in that Glaze Bay by the where the studios are, in that little area for studio artists where we can put our tiles.
There's a bunch of tiles on the shelf right now. I thought they were yours, Ursula.
They are. I have like 75,000 tiles because I did them all like 7 times because I really enjoy this class. So, and I'm an overachiever. So but the ones that are all fired, once we get them back fired, we can post them. Like Audra's gonna make us a little place where we can, like, I don't know, glue them up or with some hot glue or something. I don't know. So we can actually look at them in person. So we don't have to be like, here's the tile, and then we can't see what it is.
That's why, I wanted you to be able to see them in real life, because I can look at them and I pretty much know what's going on. Minus Dawn. I still have a chip on my shoulder about Dawn. Stupid white tiles.
So anyways, I was going to say, like, maybe before we reconvene in January, we could do like a tile assembly where we like glue them onto the board or whatever Audra gets figured out.
Sure.
We can toast them or something. I don't know.
We'll do a tile parade.
There you go. All right. So
bring a bottle of wine, make a good time of it. It's all good. All right. So enjoy your holidays, your downtime. Go get some sleep, and I will see everybody on the flip side.
Well, thanks, Matt.
Okay.
Thanks. Happy solstice.
Happy solstice. All right. Talk to you later.
Bye.
Bye.
Bye.